All right, so welcome to Math341 probability. This is lecture 15, and one of the things that Williams does extremely well is they alert us before the semester even begins when to expect the prospective students so that we can plan our schedule accordingly. And so I wanted to cover this topic anyway in probability, but this is a great topic to do when we have people visiting because it's a great way to see an introduction to statistics and modeling. What can you do with all the stuff that you have been learning? We may have some video malfunctions if I talk about some work I've done with students on Major League Baseball lawsuits. The technology just doesn't always work perfectly. It's just a fact of life. And so happy to talk to people about opportunities if you're interested in doing stuff like this. I've had a lot of students work with me, and I'll just leave it at that since it's being recorded right now. Okay, so a lot of people that I want to acknowledge who I've worked with projects over the years with, but most importantly is my great uncle, a lifetime Red Sox fan who assured me I would live long enough to see the Red Sox win the World Series. All right, so the first thing is just talking a little bit about thoughts on research. So the goal is to either take the stuff and push it forward and find something new, or take the stuff and apply it to situations that already exist. So there's a lot of different things you can do. I love building on things that I love to do. Then it's fun. And so a lot of us like sports. This is a very natural thing to go into. If you don't want to apply this stuff to sports, a lot of the stuff also could be applied to stock market and investments. A lot of it's also who do you want to work with, what kind of project, what kind of department you want to be in, what kind of work environment you want to be in. Ask questions. It's amazing how much of work comes down to asking the right question. Once you've got the right question, 95% of it is often just trained monkey work, that if you give somebody who has good quant skills, they can just go through and do it. But it's asking those questions in the beginning, that's the really hard thing. Look for connections. This is one of the advantages of being at a liberal arts college, is you are hopefully taking more than just math and stats classes. You're hopefully seeing connections between different subjects. One of my favorite lectures to give is a lecture on differential equations in the Battle of Trafalgar. Did Lord Nelson know differential equations when he came up with his battle plan against the French-Spanish Armada, or did he just have an instinctive knowledge of how to do things? So again, huge advantage to knowing lots of different things and to having a diverse group of people that you work with who can give you different perspectives. All right. So I've already mentioned a couple of times, if I were ever to become nobility and if I were to get a shield, I would have on that shield a hammer. There's lots of different ways of formulating the law of the hammer. I like the last because it's the most succinct. If all you have is a hammer, everything looks like a nail. This is terrific life advice. I think I've already told you at one point, if you listen to any political debate, it doesn't matter what question the candidate is asked. After a couple of seconds of meandering, they get into their fixed spiel that they were going to say no matter what. And depending on how good they are, it's a more natural transition as they get into that fixed point that they want to do. If there's something you're good at, you try to make anything you're given fit what you can do well. So that's one way of looking at it. The other way of looking at it is if you're really good with a hammer, go to the land of the screwdriver. If they could have solved the problem using a screwdriver, they would have. They're not stupid people. But if you have a new perspective, if you have new tool sets that they don't have, it's quite likely you can make real progress. When I was dating the person who's now my wife, some of her professors found out, wait, you're dating a mathematician? Can we talk to him? And so I ended up working on problems for the movie industry, and I applied number theory and combinatorics in marketing in ways that just were not in the perspective of the people who were working in the subject. And they had other perspectives that I did not have. And it was a really good collaboration because we didn't all bring the same skills. We had different things which we were good at, and it made a much better product. All right, so I'll skip this part over here. How many of you out of curiosity have heard of the Bill James one-loss formula? As the person who's giving the lecture, my hand better be up. When I teach abstract algebra, I can't raise my hand because I've actually never taken abstract algebra. But statistics are extremely important. Good statistics are even more important. You can come up with a bunch of ridiculous statistics. Does everybody here have at least a passing knowledge of baseball? Okay. Anybody want to guess what is the worst or one of the worst statistics in baseball?
wins and losses for a pitcher.
Close. Wins and losses for pitcher is bad because a lot of it doesn't depend on how well you do. So I will definitely give you that wins and losses is a bad statistic, but there's a pitcher statistic that's even worse than wins and losses. Not every pitcher can get this statistic. No. So what kind of statistic could a pitcher get? Say the last pitch of the game.
Oh, save.
The save. So can anybody define a save in baseball?
I mean, it means that you didn't give up a run, basically 1 inning, but it could mean you didn't give up 3 runs in 1 inning. Basically,
No. This is most of the time for a save is if you are the last pitcher of record and you come in with a lead of 3 runs or less and you never relinquish the lead, you get the save. When you hear the word save, does this sound like an accomplishment? Yes. Most teams do not score 3 runs in 4 innings. So if you have a 3-run lead with 1 inning to go, it's pretty safe. But the save sounds really good. There is another way to get a save. If you pitch the final 3 innings, no matter how big the lead is, you can get the save. One of the Red Sox pitchers got a save a few days ago, coming in with a 14-run lead and 3 innings to go. A couple of years ago, somebody came in, they only had an 11-run lead, but their team scored an additional 16 runs while they were pitching. You should not get a save for this. Now, the hope is that the number of times this happens is small. And that when you're looking at some of these statistics, yes, there is some noise, but for the most part, this is a good statistic. Do you think homework is typically a good indicator of how well you're understanding material? Yeah, but there could be a week where you just had a lot going on and the homework score for that week doesn't really reflect what's going on. You really want to be careful and make sure you're focusing on good statistics. I actually have some Williams students working with me on improving the save statistic as a research project right now. So the Pythagorean one-loss formula is a way to predict a team's winning percentage using just a small amount of data. Now, in the 21st century, this is less important than 100 years ago. How many of you have done extensive data calculations? Raise your hand if you've done some extensive data calculations. Looking at least data with at least 100 entries. Okay, and how many of you have done that by hand? Exactly. No one does this by hand anymore. You don't need to have simple statistics anymore. So in terms of what I'm putting into my model, the fact that this only needs to look at runs scored and runs allowed, well, that's no longer as necessary as it used to be. However, one of the holy grails is to get closed form expressions. So where are my econ majors? Right. How often do you have closed form expressions so that if we increase the tax rate by this percent, this will be the impact on the GDP? Do you have formulas like this? In theory. And are these formulas useful at all? Sometimes. You're being very generous, I think. You need to know a lot of values of parameters. I think I mentioned my dad was in an MBA class where they gave them an equation with 46 variables to describe what to do. And it would perfectly describe what your company should do. But he calmly asked, well, some of these variables are effectiveness of opponents, advertising. I don't even know what they're spending on advertising. How could, but isn't it a beautiful formula? Yes, it's a beautiful formula. And so you want formulas that allow you to make quick inferences. I only have so much money to spend if I'm not the Dodgers or a few other teams. How do I want to spend the money? Is it better to spend it on a pitcher or a hitter? Which type of pitcher? Who's going to have the most impact? So formulas like this, where you have closed form expressions that allow you to then see how things change, are extremely valuable. Okay, and so what I want to do is try to find statistics that describe the real world. I don't think I've shown this before. Does anybody know which bridge this is? Shouldn't be that hard to figure it out, right? The Harvard Bridge. It's normally listed not as 620.1 meters. Does anybody know what unit you normally use to measure it? Person. Anybody know the name of the person? the smoot. So in the old days, I'm not going to say the good old days, but in the old days, there was a little bit more freedom what fraternities could do with pledges. And so one of the fraternities was curious, I wonder how many times it would take for us to put one of our pledges down, mark, pick him up, put him down, mark, pick him up, put him down, mark, until we got to the other end of the bridge. And so they found it took 364.1 smoots. And I love the plus or minus 1 ear. And so smoot has become a unit of measurement. Now, when they did this, the city of Cambridge was not amused, and they painted over the paint marks. The fraternity wasn't amused, so they did it again. Eventually, the city gave up. The smoot marks survived. And in fact, they've now been immortalized, and they are now official smoot marks. And whenever there's an accident on the bridge, they report how many smoots, down on the bridge did this accident happen. Is this a good statistic? This is probably the most marshmallow question I can ask you. Why is this a bad statistic? Why is it not generalizable?
I mean, you like translate smoot into meters, but it's like not a
right. So if I translate smoot into meters, also of course I'm not sure smoot's height is going to be constant over time, right? It's just, if you want to say 364.1 meters is a smoot, okay, I could do that, but then really the fundamental unit is still the meter. But having something like smoot that you have to pick up, it is an interesting thing to think about how we choose units. Any physicists here? So the real question is, what is the fundamental unit? Is it the unit of time or the unit of distance? And so because the speed of light is a universal constant, once you choose either distance or time, you get the other one as the derived quantity. And I believe now the meter used to be defined as the length of a certain rod in France. Now it's defined as how far light goes in a certain number of vibrations, I think, of a cesium atom. All right, so the goal is to get to World Series championship rings. And so I was fortunate enough, I got to wear a Red Sox World Series championship ring very briefly. I was walking with some friends and family members and ran into a friend of a family member in Maine and was chatting about the Red Sox game the night before. And he mentioned the first time the Red Sox gave him a ring. As a mathematician, I can say the first time something happened, if it only happened once, and that would be acceptable. People understand mathematicians don't speak the same language always as other people. Normal human beings would never say the first time unless there's a second time. He used to be chief of police at a college, retired to Florida, worked spring training, and the Sox were so generous that they actually gave World Series rings all the way down to security. All right, so a couple of things that we're going to need to know. So in games like baseball, whoever scores the most runs wins. Baseball cannot end in a tie. It was decided a couple of years ago that it would be a catastrophe for a baseball game to end in a tie. So baseball games will never end in a tie. And whoever scores the most runs wins. So we'll let RS observed be the average number of runs a team scores per game. And RA observed will be the average number of runs a team allows. And then gamma is going to be some parameter that'll depend on the sport. And what Bill James discovered is that a really good predictor of a team's winning percentage, so the number of wins divided by the number of games, is runs scored to the gamma over runs scored to the gamma plus runs allowed to the gamma. Originally, he took gamma to be about 2. In fact, he took gamma to be exactly 2. The reason is this was done decades ago when you were doing things on a calculator. You can square things very easily. Nowadays, it's around 1.82 is the best value that people use. Different eras of baseball have different values of gamma. If you know your baseball history, there was what's called the steroid era, where there was a lot more offense happening. There was also the dead ball era, where pitchers were far more dominant. And so depending on which era you are, you could have a different value of gamma. You can also apply this in different sports. You can apply this in football and basketball. Does anybody know what advantage baseball has over other sports?
It's extremely quantifiable.
Well, the other sports are quantifiable as well.
But like after every play, there's a specific outcome. And after every game, there's
You have that.
It's not like dynamic motion.
Well, so if you want to try to evaluate the contribution of an individual, it's much easier in baseball. If you have a sport like football, the Buffalo Bills years ago signed a quarterback who spent most of his college career gazing at the stars. And the reason he spent his time gazing at the stars is he had no offensive line. So he was constantly under pressure. He was constantly being hurried. And what they did is they really dug deep into the data and they said, on the plays when he had time, he was actually very effective. We think he's being undervalued. And so in a sport like football or basketball, it's often very hard, hockey, soccer, football, it's often very hard to isolate the value of the individual. But if I'm looking at just team records, at the end of the day, it's a win, loss, or a tie. But and you need to know a little bit about seasons, what advantage does baseball have over hockey and basketball, and far more over football? A lot more games. Baseball used to be more than a factor of 10 than a football season. Now it's a little bit less than a factor of 10. Much more data. And so small oscillations are more likely to die out if you're looking at a long season like baseball. And so just as an example, in 2009, the Sox were 95-67. They scored 872 runs, allowed 736 for Pythagorean prediction of 93.4. Well, maybe I'm cherry picking the numbers. I'm only giving you one specific number. The Yankees, however, were predicted to be 95, but they had actually won 103 games. So, why can something like this be useful? 3 reasons. One is extrapolation. You can try to use this to predict how will you do for the rest of the season. And so maybe you've just had a couple of unlucky games. Maybe you've just had a few bad breaks. Your team is really better than your record indicates. And you shouldn't give up on the season. And a lot of times teams have actually done these calculations and they said, we might be 6 or 7 games out of first place, but our record, we don't think is a true predictor. Another is if you consistently over or underperform, they often use this to give credit to the manager and the coaching staff as to, are you able to get the most out of your players? This is a very easy formula to use if you can then change some of your numbers, how many runs you're scoring, how many runs you're allowing. You can use this to predict how many wins you will generate. So we actually have formulas that allow you to predict how many runs a lineup will score. We have formulas to predict how many runs a pitching staff will allow. And this will help you determine how valuable somebody is. The value of somebody is dependent on who else is on the team. If you look at 2004 and Barry Bonds' numbers, his numbers are just absurd. The number of times he walked was ridiculous. There's a beautiful YouTube video of what would happen if Barry Bonds never swung a bat in 2004. And they tried to extrapolate what the other pitches would be. Why did Barry Bonds walk so often? The Giants didn't have a good hitter after him. So a lot of teams said, we'll just walk him and put him on base. But if you have a credible threat afterwards, now all of a sudden you're going to see a lot better pitches because they don't want to put you on base. So again, how valuable somebody is depends on the rest of the team. So you can't just take into account, I'm signing this player with these numbers. I need to factor, what team they're joining, who else is there. But a formula like this is extremely valuable if we know it's going to hold in the future. If we can predict how many runs a team is going to score by signing a player, we have a better sense of, is it worth signing them? All right, so just basic probability and modeling. So our goal is to model some kind of observed scoring distribution, maybe something like this. And so just to have everybody on the same page, for my visitors, how many of you have seen calculus? Okay, excellent. So when you saw calculus, did they ever mention the word probability? So the reason we care about integration is integration gives us area under curves. Who cares about area under curves? Area under curves is often probability. So if I have a random variable with density p, that means p is non-negative, p integrates to 1, and the probability x takes on a value between a and b is just the area under the curve from a to b. So the mean value is just x times p of x. And then the variance or the standard deviation, how spread out something is just the integral of x minus mu squared. So if all the mass is close to the mean, the variance is going to be small. And the more spread out it is from the mean, the larger that's going to be. And an independence is knowledge of one random variable gives us no information about knowledge of another. Right? Should my performance in this lecture have any impact on the Red Sox performance tonight? No. It might have an impact on whether or not our guests choose to come to Williams, but this should be completely independent of the Red Sox performance later tonight. Okay. So here is the basic dilemma that we always face. Whatever mathematical model you come up with should capture the key features of the system, and it should be mathematically tractable. What's the problem? So what's the problem with these two statements? It's hard to do both. The more features you capture, the more involved your model is going to be, and the harder it's going to be. Did I do the comment about Galileo's experiment? Does everybody know about Galileo's experiment where he drops two balls? And the point is to show that the mass does not matter in terms of how long it takes to hit the ground. How many of you have heard of this experiment? A very famous experiment. What color were they? Why does it not matter what color they were? Yeah? Yeah. So why doesn't it matter what color they were?
It's not a feature of the experiment that ends affecting hypothesis. Unless it affects like how well you can measure like when it's there.
Okay, so do you think the color could impact how easy it is to see when it hits the ground?
Yeah.
Maybe. There is another way color could impact. So it could be maybe if the paint is thick versus thin, it could affect air resistance. I was thinking more in terms of black and white, leaving it out in the sun for 8 hours. They could be at different temperatures. And now all of a sudden, you're dropping two things with two different temperatures. You've got to be very careful to keep as many things constant as possible. When I was in grad school, I used to volunteer for psychology experiments with some friends. We would get money, then have dinner out, go to a movie, and make fun of the psychology grad students. And some of the things they did were terrible. One of my least favorite or favorites was they wanted to see how long it took you to count the number of, or how well you could estimate the number of dots on a piece of paper. So they would show you a piece of paper with some dots, you'd have 5 seconds, and they put down and they show you another piece of paper. What equipment do you need to do this experiment?
You like standardize amount of time you show.
Okay, how do you do that? How do you standardize the time? What do you need? Stopwatch. They were doing the 1 Mississippi, 2 Mississippi, 3 Mississippi. And we tried to explain to them that the counting to 5 Mississippi is not a good way to time 5 seconds. And it's just, but on average, I'm going to be constant. Okay, yes, but you're introducing all this needless noise. There's no reason to do this. And I couldn't get through to the student. And then finally inspiration struck and I said, are you the only student doing this? No, there's a bunch of us. Have you checked to see if you all count it the same way? No, it doesn't matter. It averages out. And you've got to be really careful. Sometimes it's very easy to see this is a bad experiment, that there's factors going on that you're not aware of. I really want this to be on your mind whenever you're doing things. Is there anything that's contaminating your data? Are there any things that are going on that might be causing the issue that you're not aware of? And so when Galileo is dropping the masses to see how long it takes, it doesn't really matter what color they were. If they were kept at the same temperature and immediately brought out, it shouldn't matter. But if they were sitting outside in the hot sun for 8 hours, all of a sudden you might have them at different temperatures, and you've just got to be careful for something like that. So here is a possible model that I would like to propose for baseball. Runs scored and runs allowed are independent random variables, and they're drawn from some probability distributions. So can anybody give me a reason why this model might have issues? Okay, why might they not be independent? Yeah. So if you've scored a lot, that could impact you. Do you maybe give some of your starters some rest and see what the other people can do? Maybe you put in a pitcher who normally would not get to pitch. I remember a couple of years ago, the Sox were leading, I think 10-3, 10-4 in the ninth inning, and they brought in somebody who normally they show you the pitcher's ERA when they come in, how many runs they allow on average per 9 innings. They couldn't show you his ERA. The reason is he had given up runs as a Red Sox, he just hadn't gotten anybody out yet. So it was a division by 0, and the network did not have the symbol for plus infinity. The guy proceeds to give up a grand slam. He actually creates a safe situation. He comes in with a 6 or 7 run lead, and the Sox win by 3 runs. He created a safe situation and got it. So you would never have put him in a close game the way he had been pitching. We have a second midterm for this class coming up. Unless you tell me otherwise, I'm not going to count whichever of your 2 midterm exams is lowest. Do you think all of you are going to perform as well on the second midterm? No. If you are very happy with your first midterm score, you can afford, I'm really busy in some of my other classes. I might not even take this, or I might only just do 1 or 2 problems that I'm curious about comments. So I don't think runs scored and runs allowed are independent random variables. I think this is a bad assumption. Why am I willing to make this assumption? It makes it much simpler, right? It's much easier to assume that they're independent. And the hope is that maybe things average out, right? So we have 2 possibilities. If I want to calculate the probability that one team beats another, I could do it as an integral. So I score X runs, I allow Y, and I integrate over all X and Y where Y is at most X. And again, if you haven't done multivariable calculus, it's just doing one variable calculus twice. So after you integrate with respect to one variable, then just integrate with respect to the other. Or I could do it as a sum. I sum over all pairs I and J with J strictly less than I. Which do you think is a better model for baseball? A double integral or a double sum? What do you think? Continuous or discrete? Baseball's discrete. I'd love to see the Red Sox beat the Yankees by a score of pi to E for a variety of reasons. Never going to happen. Which do you think we should use then, discrete or continuous? Discrete. We're going to use continuous. Why are we going to use continuous? How many of you have taken Calc 1? Calc 2? Calc 3? Right. So a lot of you have taken at least 3 semesters of calculus. Wouldn't it be nice to use that stuff? How many of you have taken summation theory 1? Summation theory 2? We don't have as good formulas for sums. We have a lot better formulas for integrals. And so we'll make this approximation and we will deal with a continuous model. Okay. So we'll reduce to calculating. So some of the natural questions are, what is a good choice for the densities for runs scored and runs allowed? This is one of the reasons why in this class, we've been looking at so many different probability distributions. The more distributions you know, the more likely you are to find something that models the real world. And then once we have these, can we actually do the calculation? Can we do the integral in closed form and now have a nice formula in terms of these parameters? So I probably should have asked you first, but so I guess there was a quick subliminal message. What would you say is the simplest probability distribution to start with? And it just flashed a moment ago. The uniform, right? Do you think that this is a reasonable model for baseball? All scores equally likely? No. And unfortunately, this limits the maximum number of runs you can score in a game if it's a uniform. You can't put a uniform from 0 to infinity. All right, so the uniform is out. Can somebody give me another suggestion? What should we try next? Normal? What was that? Anybody think of anything other than normal? All right. Normal happened to be next. What's wrong with using the normal? I can think of 2 issues. Yes. You can't score less than 0, so that's a problem. What else? Right now, well, you'll never score infinitely many runs, but this could allow you to score 15 quadrillion factorial runs. Now, the probability of that is less than my winning the lottery every day of the year without buying a ticket. It's extremely unlikely. And so sometimes you might say, you know what? Rather than truncating the normal, let's just let it go all the way off to infinity. Because the issue from that is going to be so small, the amount of probability to science, it's not worth worrying about. But the normal, the fact that it does give a positive probability to a negative score is a problem. I could, of course, shift the normal, and then the probability of being negative could be very, very small, but it's not going to model things well. Can you give me another distribution we could try? Exponential, which happens to be the next one. Excellent. Right? So the exponential is good. No negative scores. It's decaying very rapidly so that while I have a chance of scoring infinitely many runs or arbitrarily large, the probability is quite small. You need to know a little bit about baseball now to tell me why exponential is not good for baseball. A lot of zeros. It has too many games that are zeros. And what is the goal of Major League Baseball? No, you're close. If you're an econ major, you need to be able to answer this question immediately. What is the goal of Major League Baseball? Make money, right? Anything in the real world, almost surely the answer comes down to make money. How do you make money? Make the games interesting. But that's not the goal. The goal is not to make the games interesting for the sake of it. Now, sometimes for teams, the owner is not trying to make money. Sometimes the owner is trying to just city pride, or they just want the championship ring. But for the league wants to make money. And so we like high-scoring games typically as Americans more than we like low-scoring games. And this just does not describe how things go. And there's a lot of rule changes to try to get the games to be more high-scoring. In fact, this is one of the reasons why the shift was banned in the infield, is it was too effective in cutting down offense. So what I would like to introduce you to is the 3-parameter Weibel, which we haven't seen before. And the reason I was led to study this is because of physics classes I was taking. Have any of you seen like the Maxwell-Boltzmann law? Okay, so things similar to that and things in random matrix theory had stuff like this on my mind. This is a 3-parameter distribution. The more parameters I have, the more things I can model. That's good. Right. Now, when you look at it, a lot of these parameters are very easy to understand. They have a very straightforward impact. Notice that you never have x by itself. You always have x minus beta. Beta just translates everything down. So rather than talking about baseball, let's talk about the NBA for a moment, basketball. Your life is on the line. I actually have authority to either shoot you, end your academic career, whatnot, if you get this wrong. I need a lower bound that you are positive a professional team in the NBA will score at least this many points in a game. Can you give me a number? 0. Yeah, 0 is the safest bet to do. If my life is on the line, I'm going to go with 0. Now we can make it a little bit interesting. For every point above 0 that holds, I'll give you $100. But of course, if your number is too high, I kill you. Can you give me a number that you'd be pretty confident about would be safe for the NBA? 50. 50 is probably safe. I might be 40 just to be, but 50 is almost surely safe in the NBA. In college basketball and high school basketball, absolutely not. You sometimes have these incredibly lopsided games. But in the NBA, someone's going to score at least 40, 50 points. And so what beta does is it allows us to translate things. So rather than starting at 0, it allows us to start at, say, 50. Notice, however, that beta, that x minus beta is never by itself. It's always divided by alpha. All alpha does is it rescales things. Does it matter if I measure things in meters or in smoots? No, I can convert from meters to smoots. That's all alpha does. Alpha and beta just translate and rescale. They don't change the fundamental shape. So while this has 3 parameters, 2 of the parameters are harmless. It's the third, gamma, that really matters. If you notice, think of x minus beta over alpha as u. We have e to the minus u to the gamma, and then we have a u to the gamma minus 1. If you're thinking about integration, this is going to be really nice, right? If I want to integrate this, wouldn't it be nice if I had a u to the gamma minus 1? Because then I can make the change of variables. Oh, I have that. That's why we look at the 3-parameter Weibel. There's other generalizations of the Weibel as well that are also nice and integrable in closed form. Okay, so here are a couple of different choices. The red one is the 1, 0, 1, which is just the exponential. And the other ones, I like the cyan and the green. They're basically the same, except I translate one of them by 2. And then, the blue one looks almost like a normal distribution. And so with the Weibel, I can really do a good job modeling what we will call one-bump distributions. You go up, you go down. And if you think about scoring, you start off with maybe very few games where you score that little, and then your probability of scoring goes up and up and up, and then at some point, it then starts going down. You don't all of a sudden, at 50 runs in baseball, start scoring with a greater probability than you were before. So it's not unreasonable to expect a lot of scoring distributions will be these one bump, go up, go down. They have lots of different applications. When gamma is less than 1, this is a situation of high infant mortality. When gamma is greater than 1, this is a situation where things survive for a long time. They often use stuff like this to model, for instance, demands for movies. Most movies, the demand decays over time. The longer the movie has been out, the less people want to see it. There's a few movies that go in the other direction. They start off as like a sleeper hit, and then there's buzz about them, and people then start to see them. Blair Witch Project from when I was in grad school was one of the quintessential examples of a movie that started slow and then just expanded as time happened. So I am not going to go through the integration in great detail. The slides are online, and they go through all of the calculations. I do want to mention the gamma function because we will be talking about this next Tuesday in class. It is a generalization of the factorial function. So it's defined as the integral of e to the minus u to the s minus 1 du. And when you see this, your first thought should be, so gamma of s is defined as integrating with a u to the s minus 1. Why don't I define it as just u to the s? Why would I put the minus 1? It all comes down to what is going to lead to the best algebra. And if I want to write u to the s minus 1, I can write that as u to the s and then du over u. Why du over u? Well, if I rescale things, if I change u by a factor of 5, du over u doesn't change. That's why we have the minus 1. We're really integrating against this function du over u. We'll do this on Tuesday. It turns out if n is a non-negative integer or positive integer, gamma of n is n minus 1 factorial. This is a way to generalize the factorial function. And because we can now write the factorial as an integral, we can actually get growth rates of the factorial very easily. You can calculate the mean and the variance of the Weibel. It's just doing some integrals. And the hope is that these integrals won't be too bad to do. So the mean is alpha gamma of 1 plus 1 over gamma plus beta, and a more involved formula for the variance. So I'm not going to go through in excruciating detail. I'm going to just say basically, if we want to do the mean, it's x times the following. Well, I mentioned earlier that x is never by itself. It is always x minus beta over alpha. So let's do nothing. The way you do nothing in mathematics is you add 0, you multiply by 1. So let's look at x minus beta plus beta, divide by alpha, and multiply by alpha. And the plus beta just factors out beta times something that integrates to 1 is just beta. So that's where this beta comes from. And now I have this integral to do. So now I just change variables. And this is now a calc 2 integral to do. And so one of the reasons we can do this is we've just defined the gamma function. And so the integral at the end of the day is just gamma at 1 plus 1 over gamma. Whether or not that has a nice value is a different question, but we have defined the gamma function, and it turns out it often does have a nice value. All right. So real estate on web pages is valuable. What could you have on a web page? You could have ads. You could be making money. Now you have to have a product so that people will actually come to your web page. you have to think, what do I truly need to show? What's most important? Team name, kind of important. Wins and losses, yes. Do we need to say the percentage? No, but do you trust Americans to do division? You can look it up. Wendy's years ago had the 1/3 pounder. And a lot of people said, why would I pay the same for a 1/3 pounder when I could get a 1/4 pounder? Yes. So, living in America, we'll include percentages. Game back, well, we can always do this by subtracting. Okay, again, we'll include games back. Last 10, that kind of gives you a sense of how well is the team playing. That's not a bad statistic to have. What's the current streak? INT is interleague games, their record at home, their record on the road. And then the next one is the XWL. That's the expected win loss. That's the Pythagorean prediction. So this shows you, the level of importance of this statistic. This is one of the statistics in the expanded list that shows up. So this had been used for decades, but nobody had a proof as to why it worked, showing that it's a consequence of a reasonable model. And when I was teaching mathematical statistics at Brown, as a postdoc, one of my students brought this to my attention, and then I wrote a paper and have investigated this a lot further with many students over the years to come up with the model I'm describing to you today as to why does this work? Why does this do such a good job of predicting a team's winning percentage? All right. So unfortunately, it seems like it's cutting off stuff in the very bottom. So there's 4 possible formulas I'm proposing for the probability that a team wins. So if A wins P% of their games and B wins Q% of their games, there's 4 formulas. And they all have the same numerator and denominator. The only difference is it a plus sign here or a minus sign? Is it a plus sign here or a minus sign? And there's 4 possibilities. This is called the log5 method. I don't want to go into why this is called the log5 method. Any thoughts as to how you would determine which one of these formulas is reasonable? What could you do to try to see if the formula is reasonable? So A wins P% of their games, B wins Q% of the games. I want to try to figure out what's the probability A beats B. Are there any values of P and Q where you know what the answer should be? Okay, so if you have the team that always wins and they play the team that always loses, you know what should happen. The team that always wins should beat the team that always loses. What else do you know? So if they're both 0.5, what should be the probability? 0.5. What if A and B have the same winning percentage? What should be the winning percentage of A? 0.5. So we already know, so if P equals Q, we should get 1/2. So we could look at over here. If P equals Q, we get P plus P squared, and we would have 2P plus 2P squared. That's 1/2. So that's reasonable. Over here, with the minus sign, we would have P minus P squared, 2P minus 2P squared. That would be reasonable as well. Over here, we would have P plus P squared, 2P minus 2P squared. That's not 1/2. So we could eliminate the last 2 as they're not reasonable when P equals Q. So this is one of the things I really want you to get out of this course is doing these extreme tests to see is something reasonable. If P is greater than Q, what can you tell me about A's winning percentage? It should be bigger. What if P is greater than 1/2 and Q is less than 1/2? What can you tell me about A's winning percentage? So if A wins 60% of the time and they play a team that wins 40% of the time, what should be true about A's winning percentage? Greater than 0.5, but you can do even better than greater than 0.5. Greater than 0.6, because A wins 60% of the time against an average team. They're now playing a weaker team, so they should actually win more than 60%. So the answer should be greater than P. So I'm not going to go through all the details. There's a bunch of cases you can do. It's a really good thing to explore. You can actually show that it's the last one that works. I'm not going to go through it. It's all in the slides. You could do it as conditional probabilities. A has a bad game with probability 1 minus P, a good game with probability P. Then look at the same thing for B having a good game and a bad game. And if you have a good game and the other one has a bad game, you win. If you both have good games or you both have bad games, you play again. You keep doing it until you have different outcomes. And so this is a nice, since I do like a frequentist approach, just play 1,000 games and see how often you end in each one. So I'll leave that as a fun thing to play. All right. So what I was able to show is that if you assume runs scored and runs allowed are drawn from these 3-parameter rivals, they have the same gamma, the same beta, and different alphas depending on how many runs scored and runs allowed you allow, then the probability that you win is just 1 scored minus beta to the gamma, 1 scored minus beta to the gamma, plus 1 allowed minus beta to the gamma. So the Bill James prediction is actually a consequence of this model. And so I'm going to take beta to be -0.5. And the reason is, there was a remark earlier that, baseball is discrete, it's not continuous. It would be most natural to say my first spin goes from 0 to just less than 1, and then 1 to just less than 2, and then 2 to just less than 3. But if I do this, my events are happening right at the extremes of bins. It's much better to have things centered. Let's have my first spin go from -0.5 to 0.5, and then my score 0 is right in the middle. And then the next spin goes from 1/2 to 3/2, and then the 1 is right in the center. So beta equals -1/2 is just a really good centering. And so what we want to do now is we want to show why this holds. And so we're going to calculate the probability that x is larger than y. So again, Tuesday's class was extremely theoretical. We did 3 different proofs of what the mean was of the negative binomial. We did differentiating identities. We did linearity of expectation. We did recurrence relations. We then did sums of Gaussians without integrating and found high level ways of viewing it. Today is the day of applications. Now that we have all these results, now that we can prove these results, what can we do with them? Well, I want to calculate the probability that I score more runs than I allow. So I need to calculate the probability that x is greater than y. All right, so I want to integrate the 2 probability distributions. So I put in my distribution for x, my distribution for y, and I want to do the integral. All right, well, the first thing I do is I translate x and y by beta so that my integrals start at 0. That's not a big deal. The y integral is very easy to do. I have e to the minus crap to the gamma, and I have crap to the gamma -1. So I do a u substitution. So the first one is no problem. And so when I do the u substitution, I'm going to get 1 minus an exponential. Because the x is a density, when the x hits 1, that just integrates to 1. And now I'm left with the x integral, and now things are a little bit messy. And now this is really bad that it's being cut off down below. Let me see if I can. I'm trying to shrink this and show it. Okay, there we go. So if I go like this, you can at least temporarily see what the bottom is. I have an exponential. The first one is -x over alpha rs. The second is -x over alpha ra. They're both e to the -x, just with something different in the denominator. So I can factor it out. And when I do that, I'm going to let 1 over alpha to the gamma be 1 over alpha rs to the gamma plus 1 over alpha ra to the gamma. And then I can write the product of those 2 exponentials as this new exponential e to the -x over alpha to the gamma. Has anybody seen anything like this before, where we combine by summing reciprocals? You should have seen this in one of your physics classes. Anybody remember? Liberal arts college, I'm trying to connect to other things. Circuit theory, adding resistance. You might have seen this also in some center of mass problems. This is not an uncommon thing to have things combined like this. And the nice thing is by doing it like this, I now have a new rival. It has a parameter alpha. Well, unfortunately, I don't have x over alpha, I have x over alpha rs. Well, that's not a big deal. I can just multiply by 1, and I can just adjust things so that this denominator is going to be the same as the denominator in the x. And so when I do that, I just have to multiply by a few things, and now I get a really nice expression. So now this is a y-able, it integrates to 1. I do a little bit of algebra, and at the end of the day, I've got alpha to the rs to the gamma over run squared to the gamma plus alpha runs allowed to the gamma. And so we can substitute in for our values for alpha rs and alpha ra, because we know what the mean is in terms of those. And so if I know the mean number of runs that I'm scoring, everything now just falls through. So the Pythagorean one-loss prediction is actually a consequence of our model. So if the model is reasonable, then the Pythagorean formula comes out. And this gives you a way to estimate a team's winning percentage. Now, we know that the model can't be completely correct. There's a lot of issues that, runs scored and runs allowed are going to be a little bit dependent. The hope is that these dependencies are not too bad. All right, so choosing a year completely at random, let's look at 2004. All right, so in 2004, here's the runs scored and runs allowed for the World Series champion Red Sox. Do you think the theoretical prediction is doing a good job or a bad job? I think it's doing a pretty good job. Do you think it's doing better for runs scored or runs allowed? Allowed. Maybe runs allowed is better because that's averaging over lots of different, I don't know. But I think it's doing a decent job. And so this is where we now want to use some stuff in statistics. So if you haven't taken, a Stat 201 or any other stats classes, this is the time of year where you're starting to think about what you might want to take next year. This is a chance for me to put in a plug to take more stats classes. So one is the method of least squares. You can also use method of maximum likelihood. We want to try to figure out, is this a good fit? We want something better than what's reasonable. And so what you can do is you can look at the observed number of times you scored k runs and subtract the predicted number of times, square it so it's non-negative, and then sum. And the smaller that number is, the better job your prediction is doing. The larger the number, the worse the job. And then you can just try to figure out, are you doing a good job? What are the best values? And so here's the Red Sox. Here is the New York Yankees. Good fit, bad fit. Baltimore Orioles. It's not horrible, but some issues. But again, a lot of this is they just had a lot more games where they were scoring one number of runs than immediately to the left and to the right. It's not horrible, but how about the Tampa Bay Devil Rays? Yes, this is so long ago that they were the Devil Rays. They might not have had a great season, but boy, do they know how to decay the number of runs they were scoring and allowing. What about the Toronto Blue Jays? But the Blue Jays are Canadian. They use the metric system. No, the metric system has absolutely nothing to do with the issues here. I would actually like to assert that it's good that it's not doing a great job with the Blue Jays, because if you're doing a great job on everything, I get suspicious. If something is true 95% of the time, should all of your data have that value? No. And so the more comparisons you look at, the more likely it is that some should be a little bit off. And so this is where some advanced theory enters. So if you flip a fair coin 1,000,000 times, you expect about 500,000 hits. Would you be surprised if you got 501,216 hits? What if you had 523,000? Would that be surprising? What if you had 580,000? What if you had 630,000? At what point do you start getting surprised? So this is where the central limit theorem kicks in. About 95% of the time, you'll be within 1,000. So already it gets absurd quickly to be far away from the mean. So if I have n independent experiments of flipping a fair coin 1,000,000 times, I could ask, what's the probability that at least one set is outside that range? Well, for each time I flip, I have a 5% chance of being outside. If all of them have to be inside that range, it's 0.95 times 0.95 times 0.95 times 0.95. They're close to 1, but you multiply them enough times and it starts going down. With 5 experiments, I already have a 22.6% chance that at least one is outside. With 14, which was the number of teams in the American League at the time, it's already a 51%. With 50, it's already a 92.3%. Well, that kind of makes sense. 5% of the time I should be outside of this range. So if I do this 50 times, I expect at least 2.5 times to be outside this range. Yeah, I would be quite surprised if not even once was I outside this range. So we can look to see, was it a good fit or not? And so this is called chi-squared goodness of fit test. How many of you have seen chi-squared tests in the stats class? Okay, excellent. And so we can calculate the numbers, and at the 95% level with 20 degrees of freedom, it should be 31.4. At the 99%, it should be 37.57. And the way you determine if you want to do the 95 or the 99% is you look at your data. If the data is good at the 99% level, you do the 99% level. If your data is not good at, you should not do that. A lot of people do that. And so there's a big push not to do 95 or 99%, but rather just report the p-value. And otherwise, you can play games a little bit as to where do you want to put the emphasis. But there's something beautiful called the Bonferroni adjustment. So has anybody heard of the Bonferroni adjustment? So when you do multiple comparisons, because you're doing it so many times, you would be shocked if they were all good. So you get to expand the values of a little bit. And so the 31.41 expands to 41.14. And now the Toronto Blue Jays, which was our worst one, is now going to be 41.18. That's not so bad. 41.18 is just barely outside the 41.14. And so the Bonferroni adjustment tells us that things are looking pretty good. All right, so next thing is structural zeros. If you go to the hospital, should you get worse? Is it possible for you to get worse? Yes, unfortunately, sometimes they do the wrong surgery. And this is one of the reasons why they check things so many times to make sure that this does not happen. So when we're looking at runs scored and runs allowed, there's something that can never happen. If I tell you the Baltimore Orioles scored 5 runs against the Red Sox, what do you know about the Red Sox? They didn't score 5. And so there was the Mother's Day miracle game years ago when the Sox were down 5-0 against the Orioles at home. And in the 9th inning, they scored 6 runs to win the game, with the last 1 or 2 coming from errors. But as soon as you know that the Orioles had 5 runs at the end of the game, you know the Sox couldn't have 6. So when you're doing your goodness of fit tests and whatnot, you have to take into account that certain outcomes are unobservable. And it was the fact that I had done some analysis like this that got my work noticed by somebody in Major League Baseball. Is that, I'd like to hear more about how you did stuff like this. So it's very easy to forget to take into some of these corrections and use slightly wrong numbers. Okay, I'm going to skip the stuff over there. Yeah, so I want to talk briefly about a generalization I did with some students. And so you might recognize the names of some of the people over here, some of your classmates, as well as my son. And so we were trying to generalize the Pythagorean formula. And there's lots of different ways to try to generalize it. One of the problems I had with it is if I'm trying to predict how well I do, it doesn't seem to really take into account who I'm playing. I just look at how many runs do I score and how many runs do I allow. Well, I'd like to use this based on the team that I'm playing. So wouldn't it be nice to somehow adjust for who I'm working with, who I'm playing against? And so we came up with the following. So we take how many runs you score as the home team, and we adjust it by this factor. Runs allowed by the away team divided by R, where R is the average number of runs scored by the league. And we raise that to the first power. So if you're playing a team that allows the average number of runs, there's no change. Imagine you're playing a really weak team. What do you think might be true if you're playing a really weak team? What might be true? Yeah, you'll score more. And so maybe if I'm playing a weak team, they might allow more runs on average. So I'm going to inflate the number of runs I score by a little bit. Conversely, if I'm looking at how many runs I allow, if I'm playing a team that scores a lot, I should maybe allow a little bit more runs than I would allow typically. And so we thought that this was a really good modification to do. It's very simple. Takes into account now who you're playing. And so we looked at playoff data from 2001 to 2019. Why do you think we didn't include 2020? COVID and different season. And then they changed the rules for the playoffs after that. So you always want to be careful to make sure you're doing good comparisons. A lot of times people split data into even years and odd years. You use 1 year to build up your model and then use the other year to test things. And so what we did is we looked at playoff series and we looked at how many series were won by the home team versus how many were predicted. And then what we did is we said, if it predicts a home team should win with probability 0.72, 72% of the time, we gave the home team 0.72 of a win and the away team 0.28 of a win. And so I was, very proud when we did this. So the log5 method, that was the P plus PQ, P minus PQ, all that stuff. It predicted the home team should have won the series 83.19 times. It was observed to win 80 times. And using our prediction, and I remember doing this with my son and the data coming out, we got that the home team should win 80.18. Now again, this is just one set of experiments. These are all roughly around 80, but it was nice to see that it essentially nailed it perfectly. And again, part of that just happens to be luck, but we were happy to take that luck. It looked really nice at the end and just shows you the power of something like this. Now, you might be saying that this is not a huge difference, but when you're on the margins, just that little bit of difference in terms of how valuable is something could make a huge impact. So most of the time you might be in a situation where you're not going to make much of a difference one way or the other, but if you're just on the cusp of making the playoffs, those 1 or 2 extra wins could make a huge difference. If your team sucks and you win 40 out of 160 games and you win 20 more, that's a 50% increase, but you still suck. There's 162 games in this season. In the old days, it was less than 162. Anybody know the record for most losses on the road in the season? Anybody want to give me an upper bound? 81. 1899 Cleveland Spiders lost over 100 games on the road. Now you might say, how could that be when there were fewer than 162 games and you play only half your games on the road? The Spiders were so bad that they couldn't get enough people to come to the games to make it worthwhile for teams to travel to Cleveland. And so teams refused to go to Cleveland, and Cleveland had to play most of the games on the road. They were a horrible team. Increasing their win total by 50%, they're still a horrible team. But if you just miss the playoffs, those 2 or 3 extra wins could make all the difference. And once you're in the playoffs, anything can happen. So that's one of the huge advantages of stuff like this, is trying to figure things out. You could try to play games instead of just rescaling it. What if I raise it by different powers? If I take b equals 0, that just goes back to the original model. We're claiming b equals 1 is the best. There's a lot of reasons behind this. I don't want to go through all the algebra now. Nobody wants to see it. But it turns out if you take b equals 1, which is what we're doing, then you get a really nice symmetry that the number of wins that I predict that you have plus the number of wins that your opponent has, it averages out to everybody plays 500. Everybody wins half the time. In the original Pythagorean model, you actually don't necessarily have that. So this is a nice advantage of something like that. As a just brief summary, if you actually look at, you're trying to see how well does our predictions match the real world, typically the Pythagorean one-loss formula is within about 4 games, and we're pretty much able to do that. And the best fit values of gamma we get looking at the data from the teams pretty much aligns with what you see in the real world. So it turns out that these variables really do a good job of fitting. It seems like they are statistically independent, that everything seems to wash away. The Pythagorean one-loss formula is now a consequence of our model. And we now have a way to adjust the formula for head-to-head matchups of teams to predict what's the probability my team beats this team. And that's really valuable, especially when you're getting into the playoffs and you want to try to estimate, what are the odds that somebody wins. There's a lot of other work you can do. Has anybody ever watched returns on election night? How long does it take them to call, say, Massachusetts or the District of Columbia? Instantly. How long does it take them to call, say, Utah? Instantly, right? The battleground states take a lot more time. What if we do something like that in baseball? After 6 innings, you're up by 10 runs, we're going to call the game at this point, and everything from this point onward is meaningless. We're not going to count how many runs you score when they're putting in position players because they don't want to burn out their bullpen. So I actually had some students at Williams look at stuff like that. And basically the conclusion was it's just more work and it's basically as good as not doing it. You can apply this to other sports. You could try looking at other probability distributions. We actually looked at linear combinations of rivals. And basically all it did is it just made the math more complicated, didn't really get to a better predictive power. We have a few minutes, so I do want to talk about one last thing in baseball math, but I will just mention some general advice. Seize opportunities, you never know where they will lead. So we talked earlier about this guy. Anybody remember his name? Smoot. Does anybody know what Smoot did with his life? You could imagine Smoot being pissed that he's being used as a measuring rod. Or you could imagine that he just goes with the punches and just, try to have a good time. You can't make this up. Chairman of the American National Standards Institute, president of the International Organization for Standardization. I'm just imagining his job application. Well, I don't mean to brag or anything, but I am a unit of measurement. And it's a story. Everybody here is smart. Everybody here is talented. That's not enough in the real world. You need ways to distinguish yourself. You need ways to make connections. This is one of the great things about being at Williams. We have the oldest, society of alumni in the country. People love this place. They love helping future students. Incredibly valuable. You need to find ways to distinguish yourself, get to know professors, get to take advantage of research opportunities. I would just very briefly add, just so that these are shown for the slides, just some references. I'm going to skip the appendices. I just want to end with some slides from a different talk I gave. So we talked about calling games before they're done, other approximations. I've done multiple lawsuits with Williams students. Seems to be some kind of issue displaying things, but I'm happy to talk about these when it's not being recorded. Here was something I did in my class on the mathematics of sports. Is there anybody here who is over 21? Okay, so you guys that know about alcohol. And so you might know that there's these things called mixed drinks. So like a White Russian, depending on who's making it for you, might be 1 or 2 pots milk, 1 pot vodka, 1 pot Kahlua. I don't want to see too many people smiling who are under 21. Well, maybe you're fans of the Big Lebowski. Do you really think that the best tasting White Russian has a ratio of 2 to 1 to 1? Why do they do that? It's easier. They actually have devices in bars when you're really busy. You can put in 1 unit of something very easily. And so if you have nice integer ratios, you can make it very quickly. And so if I'm mass producing drinks, I'll do something like that. If you look at a lot of baseball statistics, slugging percentage, you get 1 point for single, 2 for double, 3 for triple, 4 for home run. These are nice integer values, but maybe they're not quite the best values. So I had some of my students looking at, is a home run, should it really be weighted 4 times what a single is? And the easiest thing to compare are home runs to triples. And the reason is, a home run clears the bases and a triple clears the bases. But a single or a double, how far people advance depends on how fast they are. It depends, was the ball hit to the right side of the field or the left side of the field? Those are a little bit more complicated. I don't want to go into all the details right now. I just want to point this out, and if you're interested, I'll send you the paper. What we have is the run expectancy matrix. Is they look at all baseball games in a given set of years. They look at how many times you have, say, runners on first and second with 1 out, first and second, 2 outs and whatnot, and see how many runs does the team score on average from that configuration. Now, this isn't really great because you might have a high offense team versus a low offense team, You might be at the start of the order when you have a lot of heavy hitters coming up versus the end of the order. This is the, well, we hope if it averages out. And so you could make it a little bit better by taking into account where you are in the order. And so if I know where I am, and then I know where I go, I can evaluate how beneficial was that play, versus what I would have expected to do. And so we also know how often are we in each of these states. We know what's the value of each state. We know how often we are, and then we can calculate what would happen if you got a triple. What would your gain be? What would your gain be for a home run? And so we can do these calculations, and we can see what are the values. We can look at singles versus doubles and see how much is the single giving us, how much is the double giving us. And it turns out, according to what we were doing, with reasonable assumptions of base running, my students here discovered that the single was being a little bit undervalued. The double is a little bit more flashy, but people advance enough bases on the single. And a lot of times, even if you get a single or double, that runner doesn't score. So anyways, this is, I think, a good place to start. I just wanted to just go like this so that the references would make it there. And so I will stop here.